Hi, everyone. Thank you for joining our webinar today, where we will be introducing the next generation dynamic imaging analysis, ANALYSETTE 28, or short for A28. With me are your speakers, Dr. Günther Crolly, and also Dr. Jeff Bodycomb of HORIBA Instruments. My name is Julie Chen Nguyen. I'm going to be your facilitator, and we will have a Q&A session in the end. Okay. Let me go ahead and transfer this to our first speaker, Dr. Jeff Bodycomb. He is our product line manager who oversees all the products that we have here. So Jeff is going to open the floor, and then Dr. Günther Crolly is going to take over, and then we'll end with Q&A where both speakers will be able to answer your questions. All right, Jeff, I'm going to pass the ball to you.
Great. So, as Julie mentioned, we're going to be talking about the next generation in dynamic image analysis, the ANALYSETTE 28, which is manufactured by Fritsch, and HORIBA is doing distribution and support in the Americas. I will follow Julie's lead and say A28, like most people do that. It's just a whole lot easier. Okay, so let's get a little perspective. If you've been around particle analysis, you'll see that there's just a large range of instruments with various capabilities. And I like to make this kind of a chart as a cheat sheet where I list particle sizes across the bottom. So this is a nominal diameter in microns, going from, say, sub-nanometer up to tens of millimeters. And then resolution of mixture components, which is one measure of particle sizing or particle analysis performance. And in the upper right corner, you're going to find digital image analysis. And that appears in, say, things like image additive manufacturing, powdered metals, and so on. It's going to be size range of a few microns up to millimeters. It is also going to give you particle shape, which is something you won't find with many of the other techniques listed here. And because you're analyzing particles one by one, you get very high resolution size distributions. So this is kind of where we're operating today, is this upper right corner, with bonus shape information. We do also have offerings and webinars as you move around this graph, just not today. So with that kind of introductory perspective, I'd like to introduce Dr. Günther Crolly, and he's been spent 16 years in particle characterization, and he's head of particle size analysis at Fritsch. And Fritsch is headquartered in Germany. Günther may mention more of this, but they make a lot of very good mills, and if you have a mill, you also need particle size analysis. So he's seen some rather interesting things in his career. So I'll turn it over to you, Günther.
Thank you, Jeff, for the introduction. Well, the first question that I want to talk about is, well, why image analysis? Well, of course, there are many, many different reasons to do this. And in fact, one of the reasons that we observe pretty often at customer sites is replacing sieves. And there are several reasons to replace sieves. Well, sieves are at the first side, or when you start with sieving, well, you find it is not very expensive, so you don't need to invest too much to start with it. But over time, you find out that well, it takes a lot of effort and it's time consuming, and so on the long run, it's really getting very, very expensive. So this is something that causes people to try to look for a replacement for sieve analysis. And one of the more ideal techniques to do so is image analysis. Furthermore, of course, there are way more reasons to go with image analysis. If you look into laboratories for particle sizing, one of the most widely used techniques of all, that's at least what I typically see in laboratories around the world, is laser diffraction for sure. And laser diffraction is very, very powerful in the micron and in the submicron range, but when it gets to larger particles, well, it's getting at least difficult or, yeah, tricky to do so. And well, for sure, you can end up also, or you can measure particles in the millimeter range also with laser diffraction, but that's not that easy. And then the question comes up, why do you want to do this? Because if you simply take images, if you have an image analysis instrument, you can cover this task pretty easily with additional advantages. So therefore, you can, of course, supplement and a laser diffraction instrument with an image analysis instrument, and so widen your possibilities in the laboratory with this technique. And of course, when it comes to larger particles, really in the several hundred microns, thousands of microns, millimeter range, it is much easier to measure those samples, those particles with a camera-based system than with a laser diffraction instrument. But just beside particle sizing itself, so the question, what size does the particles have? What is the size distribution? How does the size distribution look like? More and more people also need some information about the shape of the particle and the shape distribution. And there are a lot of examples for this. If you're looking for road building material, you want to have this material to be more angular so that it doesn't slide, the particles doesn't slide against each other. So they need to be very, very angular. And on the other hand, if you, for example, look for glass beads, you want to be sure that they are as spherical as possible. And so therefore you then need to determine and to measure the particle shape as well as the size distribution, of course. An example that is listed here on this page is the OSD, the oral solid dosage manufacturer. The size distribution for those particles, of course, is very critical for flowability and for blend uniformity and compressibility and so on and so on. So therefore, this is a very common usage of this technique, and just shown here in the lower right corner. Of course, you may have particles that have basically the same size, but they look totally different, like a sphere and a square, or a circle and a square, and they then also will behave very differently in transportation and behavior during the manufacturing process, and so on and so on. Let's take maybe a little bit closer look to replacing sieves. So as I said, yeah, it's time consuming. The sieve process itself is time consuming. Well, you may think, well, I place my sample on the sieve shaker, and then I press the start button, and then I go away and I can do something else in between. But after the whole, or after the sieving process has been finished, you need to take down the material, you need to weigh it, you need to transfer the results to a table, and then you need to clean the sieves for the next measurement again. And one major problem that you again and again see in reality with sieve shakers or with sieves is that they wear out over time. And so therefore, even using always the same sieves, you will get different results over time. And this wear out is, for example, mainly driven, in my experience, for example, from the cleaning process. So everybody who is using sieves realizes that lots of particles stick in between the meshes of the sieve. So these are sometimes very small, tiny wires, and in the small holes that are formed between those wires, the particles that just don't pass the mesh, they stick in there, and it's not very easy to get them out. And some people, I've seen people really very roughly using brushes to get the sieves clean again. And as you can imagine, this will then shift a little bit or displace wires of this sieve and make the openings in between the wires larger, and larger particles can pass through a sieve that is nominally too narrow for this kind of particle. So this means over time the results will change using always the same sieves. And you also find that it pretty much depends on the user who is using this machine, because you may vary the duration, you may vary the amount of material put to the sieve, you may add different additives, and so of course you can standardize all these factors and set up a severe and solid method, but nevertheless you have significant difficulties in the reliability of the results themselves. So reproducibility, from my experience, is not that good using sieve shakers. And at the end of the day, you typically only get a very small number of size classes. You take 3, maybe 5, maybe 7, but that's already a large number of sieves. And so for your complete size distribution, you just get a handful of numbers of sizes of size classes, and everything in between, you don't really see the details. You don't know actually how your size distribution looks like. This is a little bit about shape. So sieving is just about size. You don't learn anything about shape on a sieve shaker. Shape is pretty often important, as I mentioned before, when it comes to the behavior of a powder, the behavior of a material, how particles interact with their neighbors, do they collide easily? And here is an example for different materials: glass, CS, calcium carbonate, and talc. Critical angle here denotes the angle relative to perpendicular, so a little bit irritating here. So this means the smallest number down here means nearly vertical. So this is the angle of a wall where a powder made of this kind of particles, or of this material, will start to stick on the wall. And you see this talc sticks nearly or sticks very, very quickly when you tilt a little bit the wall of your vessel or of a funnel or whatsoever. While the glass spheres, of course, they glide much better. If you have only single glass spheres, they will roll. But imagine you have a compact material, you have millions of glass spheres, they interact, and so therefore they even stick at relatively large angles already. Yeah, the assumption mentioned here, well, we don't care about the density. So the density we assume to be not the factor that is driving this behavior here in this case. It's only the shape, or mainly the shape. So what is image analysis? Well, pretty simple. Well, we take pictures and then we analyze those pictures for size and for shape. And here is, well, a black and white example. You see here is a indication of the size range that we are talking about today. This is 100 microns in the lower right corner. And if you then look to one of those particles more closely, you see more details. You see the shape here, there are corners, and so on and so on. And of course, typically you have many, many particles here. And so therefore you get lots of data from just one image. You also see one of the things you need to take care when you're running this kind of a measurement. Here the density is of particles in the image is rather high, so many particles touch each other. So typically you try to avoid things like that. And so what is typically controlled, of course, by the software of the instrument, so that you don't have too many particles sticking together, what will influence your result. So we then have, as I said, images, and for each particle, well, each particle here, or each particle here in this image is then analyzed by the software, and for each particle, well, here in this image or in this picture, you see the one with a red rectangular around. This gets analyzed, and for each particle, you get a list of parameters: cross-section, perimeter, area equivalent diameter, and so on and so on. And since you do this for hundreds of thousands of particles, even millions of particles if you want to, in some cases, you can then make up a distribution for any of those numbers. And these distributions typically look like shown here on the right-hand side. You see that particles have a given size range, and then you can find out from those graphs, well, which percentage of my sample is occupied in a given size range. So you can have this as a graph, and you can have this as tables, of course. And besides this, you can make up something like a data cloud, where each single point, each single dot that you see on this side here represents just one particle. And then you can see, well, there is a parameter like a diameter, and there is a parameter that gives you some information about the shape whatsoever. And then you can see, you see this is more in the fine range. So the fine range gives you more aspect ratios in this case, down to smaller numbers, while the larger tends to be more rectangular, more spherical, whatsoever. One nice feature, just by the way, I will not demonstrate this, but from our software, you then, when you have a measurement done and you have saved all images, you simply double click of one of those dots here, and you get the image opened, and you see what it is. And that's really very, very helpful when you study new material, when you study some problematic material where you wonder where does the result come from, and you simply go into this data cloud and you double click and you see the image, and it's looking like this. Okay, interesting. So that's really very, very interesting. Well, how does images get processed? Well, here this is most likely artificially created particle. And this is the image of a particle on the image sensor, on the sensor of our camera. The camera we are using is a 5-megapixel camera. And when we look closer to these images, of course, you can see the pixels. Well, each digital camera sensor consists of many, many pixels. And the pixel size, for example, of our camera, so the hardware in our system, the pixel size is 3.45 microns. So this is a number you know very accurately. And then by simply counting the pixels from one corner of the particle to the other corner of the particle, and then you know, besides just the size of your camera pixel, also the magnification of the lens that you are using, you then can calculate the real size of your particle. So this is quite straightforward, but in reality, the images are not as nice as in the example shown before. Well, this is a rather extreme example that I show here, but just for clarity, I have decided to choose a particle that is clearly out of focus. So each optical system, each lens has something what you call depth of field. And when you are with your particle or with your object exactly in the center of your depth of field, you get a very crisp and very sharp image. But as soon as you are outside, so every photographer knows what happens when you are out of the focus range of your camera lens, then images get blurry, get defocused. And this one here is a rather defocused particle. But to explain the concepts that we use to determine or to define, to detect the corner of your particle, I think it's helpful to use a rather defocused particle. So I make a cross section here, the red line across this particle. And outside here, you see a rather white background, and inside, of course, it's black. And white corresponds to a gray level of your camera of around 200, 210. Completely white would be 256, would be completely white, while completely black would be 0. So down here, this is dark. Up here, this is bright, gray or nearly white. So, and as you see, there is some kind of a transition from white to black here. And now the question is, where do I place the corner of my particle? So this is what you then call a threshold. And so you can set this here to, I have colored lines here. I hope you can see those colored lines. Here is a blue line with a gray value of 150, and then if you go perpendicular down to the pixel numbers, or to the x-axis, basically to the size axis, down here and down there, you find here the size of the particle. And if you change this threshold from 150 to 100 and to 50, you get different diameters for your particle, of course. This is here in the picture. Well, where is the corner? Is it more here where it turns completely black, or is it more outside where it is nearly completely white? So in this example, I have these 3 numbers, and the red line indicates where is the corner for a threshold of 50, of 100, and of 150. And if I then look the numbers, or I look to the diameters that I get, so I use here as an example the minimum Feret diameter, 460 microns, 508, and this one here is 560 approximately. And so you see there is some change when you shift the threshold. So therefore, you always keep it constant for a given task, for a given system that you examine. And how to set this? Well, there are different possibilities. You can set it automatically, or you can set it manually. So from my experience, setting it manually is very, very helpful, because the human eye is very, very powerful when it comes to determine where actually is the corner of a somewhat blurred image. This is really very, very helpful. But anyway, whatever you do, in my personal experience, really, it is very important or super helpful to have a possibility to see in the images where this threshold is located, so that you can decide if this is a reasonable position or if it doesn't make sense. So therefore, it's very, very helpful to have a superposition of the particle boundaries that you see, as I have shown before in the image with the red lines, and the original raw image that you have taken during the measurement. This should be always possible, in my opinion. Maybe a quick word about dynamic versus static image analysis, because there are also instruments available that do the task on basically static sample. While in a static image analysis system, you have particles placed typically on a microscope slide. They are stationary, of course, they don't move at all. And typically then the camera or also sometimes the table, it depends on the system, is scanning across a wider range of this sample. But nevertheless, the number of particles that you can detect with this kind of instruments is very, very limited. And of course, as you can imagine, preparation here is again a challenge, because also here, imagine you have a powder and you put it to a glass surface, and you want to prevent that particles stick together, and you want to have a rather homogeneous distribution or density across the whole area. So this is for sure possible, but it's not that super straightforward. When you have a dynamic image analysis system, the particles are moving, they are flowing, they are falling, they are transported by a feeder. So you can have a large amount of material, always a little bit depending on the material itself, of course. So it's always, yeah, what actually are you measuring? But it's falling down in a continuous process. It's the imaging takes place all the time, and you get a huge number of particles and therefore data. So this is a small animation how this works. So you see there is a funnel filled with particles. The feeder, vibrational feeder, is transporting the particles to the front end, and now it's falling down, and we are now moving to the position. So we are now the camera that is taking the images, and from the back side of the particles, there is a flashlight that are illuminating the particles from the back. So what we actually get here on the left-hand side, there is one example shown. What we actually get is the shadows. We picture the shadows of the particles, and depending on the illumination system, you get a really very nice and sharp images that are then analyzed by the software. So I think this is the point why I would like to hand over again to Jeff, because it's more going to applications.
Thank you very much for that. And that's a great segue into kind of some details about the measurement and what you're going to see as you make a measurement in practice. You know, a lot of Günther's skill is packed into the instrument, which is rather, which makes operation much easier. So now I'm going to start with something complicated, which is when you analyze an individual particle by image analysis, including with A28, you're going to get a very long list of result parameters available to you. And the next question is, what do all of these mean? I want to really just encourage you, if you're working with A28 or with any other image analysis system, you want to check the manual for how these numbers are calculated. And this is important also when you're communicating results with other groups. So let's start with kind of something that seems kind of easy and turns out to be less easy than you hope, the particle size and the aspect ratio. And in this slide, I really show two measures of size. The Feret, which refers to really the measurement of the size of the particle with a set of calipers. And I have a maximum value, which is this long stretch here, and a minimum value. So I just rotate my calipers around till I find the smallest size. And you can report either one. There are other size measures around the particle area as well. Now, next is a measure of shape. And so I say aspect ratio, and say everybody says, well, I know what aspect ratio is. That's the shortest dimension of the longest dimension, or vice versa. So there's two definitions. And then which dimensions are you comparing? And so in the A28, it is the Feret min over the Feret max, which is extremely useful measure of aspect ratio. And the reason I point this out is I've seen about 6 or more different definitions of aspect ratio across various instruments. And so this is an important fact when you're communicating about results. It doesn't really change the results too much. You want to make sure you're using the right terms. Moving on, for beyond aspect ratio for particle shape, and that's one of the exciting things about image analysis, you can look at something convexity, which is the convex perimeter. So I have a particle perimeter that just goes around the edges of the particle, and I have a convex perimeter that will be like stretching a rubber band over the particle. So I just skip this long detour inside the particle here. And so that you'll see the convex perimeter matches the particle perimeter for a circle or other ellipse. And as the particle surface has more variation, that value increases, and you express a convexity as the convex perimeter over the particle perimeter. Okay, now you have different fits to the particle shape. You will see some analyses where you'll have a circular fit, which you'll use for some size parameters, or an elliptical fit, which is you could use for both size and shape parameters. Notice the ellipse has an aspect ratio. These are somewhat less sensitive to pixelation, which is fun for the smaller particle sizes. And you can look at something like convex perimeter that really follows the perimeter, and you would want to make sure you have quite a lot of large number of pixels in your particle to follow those details. So I kind of mentioned briefly that we have a lot of different parameters to put out, and then I take one. So I have one particle. I don't know, I showed you a list, maybe 10 out of dozens of parameters. Now I repeat the measurement over many, many particles, and you have just this immense mass of data. And as Günther alluded, there are some tools in the software that let you get at it. And the first one is kind of in the upper right, where I have a point cloud. Here I plotted, I have to, aspect ratio as a function of the minimum Feret. So I have a particle size across the bottom and a shape across the left. And you can see how there's a wider range of aspect ratios for the smaller particles compared to the larger particles. And this is where you would start clicking on single points to look at what some of these individual particles look like to give yourself an intuitive idea of what is happening. We can summarize that data into a size or shape distribution, either a differential shown here as the bar chart, or a cumulative distribution shown in this graph as a line against the right axis, or as tables, and finally summary statistics. So this is a close-up of a point cloud. I used two different measures, circularity and minimum Feret. And there's another effect I wanted to show you, which is as we got to the larger particle sizes, there are fewer particles for this particular sample and many more small particles. And so you'll see noisier data for shapes for sizes over 1.5 millimeters. This is just a reflection of the smaller number of particles. It's just two parameters. There are many more. I generally stop thinking after 2 or 3 dimensions, so I'll stop here. A close-up of a size distribution. This is your usual friend in particle characterization. You have a quantity as a function of particle size across the bottom. And you'll have a cumulative, so in each, differential across the left. So in each bin, this tells me a relative amount of particles, say in that 400 to 600 micron range compared to the amount of particles in that, call it 1600 to 1800 micron particle size range. And we have a cumulative plot against the right axis, against the left axis. 100% of the particles we analyzed are less than, say, 4 millimeters. And if I go over here, I don't know, call it 10% of the particles we looked at are less than 350 microns. We can report from this D10, D50, D90, as well as mean sizes and so on. Well, we can also play that game with particle shape. And in some applications, the shape distribution matters. So here I plot the cumulative against the left axis, the differential against the right, as a function of aspect ratio rather than particle size. And I mentioned sometimes it matters. An example is if you're looking for the fraction of broken round particles, you'll see quite a jump in the aspect ratio for broken particles compared to whole spheres. Another tool is to plot particle size across the bottom and then shape across the left, which I do here. And you can see here that the circularity is somewhat higher for these small particles and then falling as they get larger. And as predicted from that point cloud, they get quite noisy where I only have a few particles. So that shape information, because the number of particles tends to fall off. Well, the next natural question is, we can display all this data. Does it make any sense? And can I tie it back to some known material? The short answer is yes. This is a measurement of the White House IA 025 glass bead standard. And pretty much you can read as well as I can. D50 364, we measured D50 at 366 microns. D10 at 254, we have a result of 246, which is just within the bottle tolerance, which is tighter than you would expect in truth. That would get into discussion of uncertainty, probably beyond the scope of today. And 520 at D90, we measure 528. So yes, we have answers that match what you expect. Let's move to something that's reasonably interesting. This is and really interesting in the sense of looking at these different size measures. This is a mixture of seeds, and it's several different plant seeds, and so they're different sizes. If you plot the size distribution, on the left I show a quantity as a function of the minimum Feret diameter, or the width of the particle, and you can see almost all of my seeds have about the same width or fatness. But if I plot quantity as a function of maximum Feret, which is quite often the length, there's a little difference because of rotation, which we'll skip for the moment. You can see two distinct populations, which is good news because there were two different kinds of seeds in there. And we had pretty nice repeatability. And so with this kind of measurement, you can start asking yourself, do I have the right ratio of seeds in my sample for my next production lot? Something go wrong in the mixing process or somewhere along the way. So that's one sort of application of the image analysis where the multiple length measures become quite entertaining, and you can also have the nice resolution, the size distributions. Moving on to something that is kind of in the news a fair amount is our metal powders used in additive manufacturing. And those tend to be fairly fine powders, kind of 30 micron size range, and you spread them across a bed and you sinter them to make parts. There are two interests in here. The one is, of course, that main particle peak, which is all those 30 micron particles you expect, and then the long tail showing that, hey, you know what, this particular sample has a significant amount of particles with sizes up at 300 microns and even one going up to 500 microns. And these additional large size particles can create errors in your 3D print. Weakened parts, voids, you'll have flow problems that create voids and so on. And so as you recycle this material, you want to monitor the appearance of these larger size particles. And so here we're using the dynamic image analysis to stare at the large size particle tail, large particle size tail. This is another metal powder, and here we've moved up in size range to about 100 microns or so, and for D50. So this is not used so much in 3D printing. It's probably metal injection molding powder that we had. We see quite nice repeatability. This is a larger particle size. In fact, the distribution is a bit broader. Again, in metal injection molding, you are still interested in things like powder flow, how fast the powder flows into the mold, and that's going to be affected by both size and shape. So I mentioned a couple of fairly uniform samples where we had the two metal powders. We really expected all the powders to form a single peak in the size distribution. We had the seeds, which is a mixture of two different distributions. And then I want to talk about fertilizer. And this is a fertilizer sample with a very interesting point cloud. There really are, and I'm plotting aspect ratio on the left as a function of minimum Feret diameter across the bottom. And you can really spot two distributions. So there's a whole bunch of particles down at a fairly small size and a fairly low, a dense bunch of particles out at 1.7 millimeters or so. And so you have two distinct populations. They almost seem to have a distinct shape distribution. And this will come up quite often when you're doing a blending operation, and then you want to make sure things are blended. The blending was correct, and then you'll get to worry about demixing. So I can show the two plots in two different ways. On the left, I show a volume-based distribution. You can see the Q3 if you squint, and you see a single peak. But if I plot the number-based distributions, which is more similar to the point cloud, I can see two distinct peaks. And this is something we've talked about in other forums, but if you look at the quantity of particles by mass, that's really a volume-based distribution on the left, and that's what naturally falls out of, say, laser diffraction data or a sieving analysis. And it's a little bit numerically hazardous to convert over to a number-based distribution. Since the dynamic image analysis does particle by particle, it's inherently a number-based distribution. We're converting to volume. And so it's much easier to resolve this small particle peak in the number distribution. So these small particles, they don't count much for the overall mass of the sample, but there are a lot of them. If fines are important, and there are a couple of reasons they would be, then you would start looking at the number-based distributions. And examples would be if you're making a slurry, your slurry viscosity will be affected by the presence of fines. If you're concerned about dust, that's that's something where tracking the fines would be important. So you're going to have a lot more dust problems with the very small particles here than the 1.5 millimeter size granules. So here is a more dramatic shape as a function of size plot. On the left, I have the aspect ratio for each size interval, and then the minimum Feret diameter. And you can see that the aspect ratio is lower for these fine particles compared to the larger particles. And so that may give you some further information about how they're generated. It certainly is useful to know kind of what you're up against, and shows one of the options with this kind of data. I don't have much left. There are kind of common questions. How many particles, minimum particle size, maximum particle size, and accuracy. I think I addressed the last one with the standard. And then I'm going to talk a little bit about how many particles, because that gets complicated. There are a couple, there's one rule that I like, which is in USP 776, which tells me how many particles to use if to find the mean size if I have a desired uncertainty and I know the width of my size distribution as a standard deviation. And I have a confidence coefficient, and I can use this equation and extract out the number of particles measured. Just to jam some numbers in there, if you have a standard deviation of 20 microns and you want an uncertainty in your mean size of plus minus 5 microns, you must measure about 60 particles. Implies a normal size distribution, more than 30 particles, and a known standard deviation or width of your size distribution. There is a similar rule for estimating standard deviations. Again, you need a lot more particles to start learning about more than the mean. To illustrate this, I did some numerical simulations. I took a overall distribution of particles and randomly sampled them, and then plotted, these are all volume-based distributions, all of the particles, and I did just 50 particles, that's the red. Measurement 1, I kind of got exactly what you expected. Measurement 2, because I was unlucky in my choice of particles, I did not get the same cumulative distribution. And if you plot the differential distributions, you see it's all spiky for the 50 particles compared to the blue of the entire population. So that spikiness is often a sign that you haven't looked at enough particles. If you measure 400 particles for this particular sample set, now it's pulling out 400 particles at random twice, I get almost the same cumulative distribution, and it matches what I expect. And my differential distributions are much smoother. And you'll notice the differential distributions I showed you were even smoother than this because we're looking at mammoth numbers of particles with a dynamic image analysis. It's just a very fast way to flow particles in front of the camera. So a quick comparison with USP. This on the left is really a plot of the estimated uncertainty. And you can see a black calculation. The number mean follows my expectation exactly, and the bottom is the number of particles we measured. Sorry for that. So as I measure more particles, my uncertainty goes down, so I have more precision in my measure. If I look at volume mean sizes, then you can see that my uncertainties are higher than expected from USP, which is fine. USP did not make claims about this calculation. And if I look at median sizes, I need fewer particles to get the same uncertainty, which kind of points you to the popularity of D50 as a size, as a measure of central tendency for particle size distributions. You need fewer particles. Quick performance graph to take home. This will be on the website under webinars. And so I have the number of particles required across the left, width of the size distribution. If I want an uncertainty over the mean, about 5%. And kind of tells you that if you have a fairly large standard deviation over mean, which is quite common, you might need 1,500 particles just to get a 5% uncertainty on your mean size. If you want more details about the distribution, like D10 or D90, you need to measure many more particles. Again, this kind of drives home why we're really having the particles fed and getting concerned about measurement speed. So kind of concluding comments, image analysis, great tool for replacing sieves, determining particle size, particle shape, supplementing other techniques. We didn't get into that too much, but it is orthogonal to laser diffraction where the size ranges overlap. You do need to, like in all particle characterization, make sure your sample prep is good and you obtain a representative sample. And you want to make sure you have reasonable material behavior. So for example, if you have a lot of clumping, you may find yourself in a bit of trouble. We have ways to fix it, but that's something to keep in mind. And ensure you measure enough particles. And that last point, because image analysis is slower compared to the ensemble techniques, it's a question that comes up, and dynamic image analysis in A28 is a way to get to just overwhelm that question by using a statistical sledgehammer. I'm going to say thank you here, and I guess I'll leave this slide up in case I need slides for questions. Turn the question and answer period over to Julie.
Thank you, Jeff, and thank you, Günther, for such a detailed talk about the hardware and also the application. So we do have a few questions that came in, so feel free to jump in if you want to take this one. What is the accuracy of this technique compared to other particle sizing methods? And part 2 of this question is, can this technique be used in line?
Okay, so yes, so the accuracy. All right, so I'm going to answer that in 2 ways. The first is, if you look at IA025, which is a spherical glass bead sizing standard, then we hit the tolerances on the standard, which includes some issues with some concern about riffling from bottle to bottle, and that measurement across multiple techniques. Yeah, so we can do very well with something like that. All the particles are round. It is well sampled. Whitehouse takes care of that, and so we do quite well. The accuracy in the images is on the order of a handful of microns at worst. It's probably 1 micron. That might be a Günther question. The next, and I wouldn't worry about that too much, because the next part of my comment, the next problem is if you measure enough particles. For example, with this Whitehouse stereo, I think we measured 100,000 particles. If I measured 1 particle from that standard, even with the best, craziest instrument possible, I would not get the right values for D10, D50, D90. I only measure 1 particle out of the distribution. And so the speed of the analysis, which lets me get to 100,000 particles, is what can get me to these accuracy values. If you don't need this tightness, you can measure fewer particles for faster measurement. And while I have my soapbox, I'm just going to mention sampling. If someone sends you a drum of particles that have been vibrating on a truck for the last 500 miles or 1,000 kilometers, wherever you are, then you're going to find the large particles on top and the small particles on the bottom. And if you scoop off the top, you're going to get the wrong answer. And so you need to draw off random spots in the drum. There are tools for this. They're called a drum thief for that example. And then you'll need to split the sample with a riffler. Now, Whitehouse has done all that for us, so this is a great check standard because of all that. Yeah, and so your accuracy depends. If you get me a good sample, I can do very, very well in terms of accuracy, and we can help ensure you get a good sample.
Thank you.
Yeah, maybe a quick comment from my side also. Yeah, Jeff basically covered everything. The typical answer to this question, what is the accuracy of this method, is it depends on your sample. If you have a nice sample, the right size range, you have chosen the correct lens for this, and you have perfect feeding conditions or good feeding conditions, then it is very, very accurate. Because what you see really, and that's the nice thing with this technology, you see the images, you can look at it. These are very high quality lenses that we are using, so-called telecentric lenses that give you a very, very not completely, of course, but nearly distortion-free images. There are some limitations, of course, but in general, it is very accurate. But if you are at the corner of the possibilities of the instrument, of course, then you lose accuracy. So some people believe when you look to the size range that you can cover with this instrument, or in general with this kind of instruments, not only this one here, but similar as well, and the measurement range starts at let's say 10 microns, 5 microns, 20 microns, whatsoever, and then you have a sample in this size range, and then people still ask for super accurate information about shape. But of course, then you just have a couple of pixels where you can determine, well, there is something, but I cannot tell you if the sphericity is 0.72 or 0.79. So there are then, of course, limitations. Maybe about inline, well, this instrument is not designed for inline. This is a typical laboratory instrument. With some effort, it is of course possible to do so, to implement it or to integrate it into a running process for doing inline measurement. The challenge then typically is to get the correct sample. This is sampling again, the correct sample out of your material stream and feed it to the instrument.
Thank you, Günther. So I want to go ahead and add the information from Icon 2. This is an instrument from Innopharma that can be used both inline and at-line. It is completely different from A28, though they are both image analysis technique. Another question that came in is a little bit long, so I'm going to go ahead and read that. Do you think this technique can be applied in the characterization of inorganic microparticles, such as adjuvants? And then I'll read the part 2 of that question. Adjuvants in a biopharmaceutical product. In this case, they have a product that's in suspension and has quite large of an amount of particles contained. So do you think this technique can be applied in the characterization of inorganic microparticles in biopharmaceutical products?
Yeah. Boy, you just know I'm going to take this one. Okay, so yeah, so let's talk about adjuvants for a moment. So most adjuvants I've encountered run down into the hundreds of nanometers in particle size, and so image analysis is not really applicable technique. There are a few that are fistful microns I've encountered, but nothing large enough for something like this. But you mentioned inorganics and pharmaceutical, and I'm going to point out that there are a fair number of excipients with fairly large particle sizes, and those are amenable to analysis by dynamic image analysis. And you know, so in excipient you have a lot of, well, I should say in solid dosages you have a lot of particle handling processes. You know, in tablet manufacture or in the larger particulate formulations, and all of that is very amenable to analysis by dynamic image analysis. You can get some details you can't get otherwise. Your particle flow you can correlate to shape information, and if you know, and if you've ever tried to do a flowability measurement on particles, you realize it's just not really a routine thing to do. It's a very valuable information, but this is just a whole lot simpler and more repeatable. Yeah, so I'd say no on the adjuvants, but I'd say both organic and inorganic excipients, particularly for solid dosages, this is very, very applicable.
Thank you. And if we didn't address your question, please don't be afraid to email us at labinfo@horiba.com. So what is the range of the multiple lessons that's included in the A28, and what is the combined size range for this instrument?
Yeah, I think we might be diving into some details that aren't generally useful. And I'm really apologize. Günther, what is the overall range of the instrument?
Well, the overall range of the instruments is about 5 microns. What is tough, to be honest? About 5 microns up to 20 millimeter.
Yeah.
Combined range.
Okay.
Really combined range.
Yeah. And I think really as we get into those details, it becomes very application specific.
For sure.
Yeah. So let's take that discussion offline into what you're looking at and what you're trying to learn. Yeah. Sorry. I've also watched the clock. Yeah.
No problem. Yes, I do want to honor your time as well. Okay, so I think we are going to conclude our webinar. Thank you so much, Jeff and Günther, for your time. Again, if you have any questions, feel free to email us. But thank you so much, everyone. Thank you, Jeff. Thank you, Günther.
Okay, thank you very much, everybody. Okay,
Thank
bye.
you. Bye.
Bye.